Question 7 then was particularly challenging. So we're given this function f of x equals ln x squared for x values of x not equal to 0. And in part A we are asked to find the derivative and show that the derivative f dash of x equals 2 over x. So this question is essentially about the chain rule. So if we have a function f of x which equals to u of v of x, remember that the chain rule says that the derivative f dash x will equal u dash v of x multiplied by v dash x. So in the context of this question, this first function here is the ln function itself. So what we're going to do here is find the derivative of the ln function, which we should remember is 1 over. So if we were differentiating ln x, then we should remember that the derivative of ln x would be 1 over x. However, here we're not finding the derivative of ln x, we're finding the derivative of ln x squared. So we would take u dash as 1 over, and then we would keep v of x. So v of x here is x squared. And then we would multiply it by the derivative of what's inside the brackets, or the second function here, which is x squared. So we would take the derivative of x squared, which is 2x, and we would multiply those out, and we should be able to see that that simplifies just to 2 over x. The second part of question 7 was particularly hard, and we are asked to find the value of d where we know that there is a tangent to the graph of f at a point P which passes through another point Q. So this is a calculated paper, so the first thing you probably want to do is just sketch the graph of ln x squared, and if you do that it looks something broadly like this. So what this is saying is the tangent to the graph of f at some point P passes through another point. So Q1 negative 3 is down here somewhere. So in essence we can see that over here there will be a tangent at some point up here, such that if we extend that tangent it would also go through this point here at 1 negative 3. So what we've got to try and do then is find the value of d, which is the x-coordinate of d at this point here. So the key to answering this question then is thinking about the gradient. From the first part of the question, we have already found the gradient function f of x equals 2 over x. So we know that at this point P, because it's a tangent, we can use the gradient function to find the gradient at that point. So we can find that f of d would be 2 over d. That's just substituting in here our input into the gradient function. So we know that the gradient at the tangent is 2 over d. Now, we can also find the gradient another way, and this is kind of the old school way that you would have seen in GCSE. So we've got a coordinate here, which is 1 negative 3, and we've also got another coordinate here, which is d, f of d. So our input is d, and f of d, if d is our input, our function would be ln d squared. So we can find the gradient by finding the difference in the y's. So y2 minus y1 over x2 minus x1. So in this instance, y2 is negative 3. So I would say that negative 3 minus y1, which would be ln d squared, all over x2, which is 1 minus x1, which would be d here. So this is an expression for the gradient, which I know must be the same as the instantaneous rate of change, or instantaneous gradient at the point d, which is 2 over d. So these two statements must be the same. Therefore, I can expand, so I can say that d multiplied by -3 minus ln d squared is equal to 2 multiplied by 1 minus d. And given this is a calculator paper, you can graph these, and you will find that on the left-hand side we have got a cubic, which is doing something like that, and on the right-hand side we have got a linear function, which is doing something like that. So the solution will be at the intersection here, and we are trying to find the x value. So obviously in your calculator you're going to have to put in x instead of d here to graph that, but you should be able to find the intersection, which yields a value of -1.31.